Swayam Prabha. Digital India. Educated India.
Okay, welcome to the 7th Gian lecture in high fidelity Lattice-Boltzmann methods. So today we have a very central lecture on the asymptotic analysis. This is how you really analyze the Lattice-Boltzmann method, so to see how it actually behaves and how it actually solves the equation that you want to solve. Some of you who may have studied the Lattice-Boltzmann literature a little bit already may have heard about the Chapman-Enskog expansion that is often used there. Anybody familiar with the Chapman-Enskog expansion? Hands, please. So a few hands. We see a few hands. Yeah. So if you study the literature, this is what you often see. So the Chapman-Enskog expansion is kind of has a connection, actually, I could say, with GPUs. Yeah, very abstract one. GPUs are actually invented for doing computer graphics, but now we use GPUs for solving the Lattice-Boltzmann equation. Yeah. And the Chapman-Enskog expansion was also used for something else and is also misused. So it was used for finding the connection between the Boltzmann equation and the Navier-Stokes equation, which we also want to do here. But now we want to, in the Lattice-Boltzmann method, we want to find the connection between a discretized Boltzmann equation, a numerical method, and the Navier-Stokes equation. So the reason why this is a little bit a misuse is that the Chapman-Enskog expansion assumes a finite size, fixed size of the molecules, yeah, and it scales the system up to infinity, so to infinite Reynolds number, to see that there is a hierarchy of equivalent partial differential equations like the Euler equation and the Navier-Stokes equation. So even though this is also done for the Lattice-Boltzmann method, in the Lattice-Boltzmann method we have a different aim because we always have a fixed Reynolds number. Yeah. So the thing that is not fixed in our setting is the size of the discretization. So what is actually small? So in the Chapman-Enskog expansion, the small size is fixed and the large size is scaled. And this leads to somewhat other results that we like to have. So, and this is all I'm going to say about the Chapman-Enskog expansion. So there is reasons why we do it in a different way, not using the Chapman-Enskog expansion. But of course, if you look into the literature, there will be a lot of Chapman-Enskog expansion. Now, today, you learn an alternative way of doing this that is, in my opinion, more appropriate for actual numerical methods. So the challenge that we give us today is to derive, again, the partial differential equation solved by the D2Q9 lattice BGK method. So, to remind all of us how this looks like, this is our stencil. Can also be drawn more beautifully. We have the populations F01, F0 minus 1. Here, of course, F10, F minus 10, F minus 1, 1, F minus 1, minus 1, F1, 1, and 1, minus 1, and of course f0, 0. So this is the thing that we always use with Miller indices, and we use two indices, Fij, with I and j being the elements in minus 1, 0, and 1. So a few things we have already seen how we do the derivation, but today we'll do it with more precision. So we start from the lattice-Boltzmann equation. By the lecture-Boltzmann equation, we term this now 8.1. Oh, it's not lecture 7, it's lecture 8, right? It's lecture 8. What am I doing? So this equation looks like this. We put everything on one side. So 0 is Fij. So this is the before collision state. X plus IEX plus JEY. And this we multiply with a half step in space, delta x half. And we have a half time step plus delta t half. So this is, we store our populations in between lattice nodes and in between time steps. Yeah. So this is the pre-collision minus the post-collision of the previous one. This is x now minus IEX plus JEY delta x 1/2 and t minus delta t 1/2. So we've already discussed, this is the post-collision, we have already discussed that we shift the populations to the states in between time steps and in between collisions. So basically what this means is that the previous post-collision state is simply turned into the next pre-collision state, yeah, and therefore the entire thing is equal to 0, right? So now we have to combine this with a collision operator, and this of course works for the different collision operators we are still going to discuss, but for the time being we look at the BGK collision operator, which is our equation 8.2, and this Fij after collision at the position x and t minus Fij before collision, so there's no asterisk here, x and t. So now this is at collision time and at the nodes. This is equal to omega the equilibrium minus the pre-collision state. So this is how the algorithm works. So the entire equation here can then be Taylor expanded. Taylor expansion of the equation 8.1 at x and t. So x and t are collision time and lattice nodes, yeah? Location and time of collision. We call equation 8.3. So we have 0 on the left-hand side, and this goes into a triple sum that I write as one sum. So we have an index m, an index n, or a counter m, and counter n, and counter l, and we'll count the time with m, the x position with n, and the y position with l, and all of them go from 0 to infinity. So this is the usual Taylor expansion. I hope everybody is familiar with this. So this is m factorial, n factorial, l factorial. comes into dx half n plus L. So dx half, because we go half a step, half a step. We also go half a time step, dt half by the power of m. And then comes all these derivatives. So the mth derivative in t, the nth derivative in x, and the lth derivative in y. So here we still have I by the power of n, j by the power of L for Fij. So I don't write that this is at x and t because this is our development point. So okay, we have here I and j together with this. So this dx, this gives us basically the derivative, right? And here we have a minus in front, so there comes now a minus. And then we have all these guys with in negative direction, always with a minus. Yeah? And so we'll have minus I by the power of n. Yeah, you see this goes positive and negative depending whether n is odd or even. And the same thing for j minus j by the power of L. And then we also have this thing here, yeah, that comes with no I, but still has a minus in front of it. So we still have minus 1 by the power of m. M is the counter for the time, and this goes into Fij after collision. Okay, so this entire thing is a bit complicated. We are going to call this T because we would later want to take moments of this, and then I just want to write T. So also reminder on raw countable moments that we've introduced some time ago. Raw countable moments. By the way, the expansion that we do here is very important that we do them on raw moments, yeah, and on countable moments. So I've seen many students then later think, okay, we can do this, for example, with central moments, but it is not easy to do an asymptotic, this Taylor expansion with central moments, because central moments are defined pointwise. So the central moment in the other, at your neighbor is a different central moment than here, because it's defined according to a different velocity. Yeah. So as much as I like to use central moments in this type of analysis, we always need to do this in terms of raw moments in the fixed frame of reference. Yeah? So this needs to be the Euler frame and not the Lagrange frame. Otherwise, it doesn't work. So therefore, raw countable moments. So again, you have seen this many times now. We count from -1 to 1 over Fij, I by the power of A, J by the power of B. And this is the pre-collision state, and also we can do the same thing for the post-collision state, which is simply the same thing, just for the post-collision populations, I by J by P. And then we also introduced this overbar version, yeah, and the overbar version can now be done the same way as we did it for the populations, namely that we have the average between the post-collision and the pre-collision states. So this in half. So one thing more that we need to define, namely the collision moment, omega AB. the collision moment is the sum over ij from minus 1 to 1. And now it's just the difference between the two, I by the power of a and j by the power of b. So we have once the sum, and 1/2, and now we have a difference. So this is a little bit asymmetric. We could have defined it in a different way, but it's now defined this way. Here we take a half of it, and here we take the entire thing. Yeah. So we need these definitions for later. And now what we are going to do is we're taking moments of this equation 8.3. So this equation where we defined everything inside here just as t, which means we have 0 is equal to minus I and j from minus 1 to 1 t by times I by the power of a and j by b. So we take the moments of the entire equation. And upon doing this, we need to write a little bit smaller because this takes now up a lot of space. So what we have here is the sum over I j from minus 1 to 1. Then we have the sum over m n l from 0 to infinity over 1 m factorial n factorial l factorial. So we have d delta x half by, not by m, I always confuse this, n plus l. So the x counter and the y counter. Then we have dt half by m. Then we have all these derivatives, dt, the mth derivative, dx, the nth, this is n, yeah, dy, dl derivative. And now we have fij. And here comes I. So I to what power? We have seen in this equation up here that we have to count up I with the counter n. But in addition to this, we also have the moments. Oh, yes. So we have the moments by the power of, a. We have I by the power of a and j by the power of b here, right? So we'll put. So what we have to do is we have to add a to n, and we have to add l to b. So, and the same thing goes in the other direction too. Here we have I by the power minus I by the power of n, and we have I by the power of a. So there's a minus here in front. Then we have minus j by the power of L and j by the power of b, and then we have minus 1 by the power of n fij after collision. So you see, we can rewrite this here as I by the power of n plus a and j by the power of L plus b times minus 1 by the power of m plus n plus L. So we take the minus 1 out, right? And we have the other one, I by the power of n plus a and j by the power of L plus b. We have them in the same way as we have them here in front. Do you see this? So with this is what you should identify here now is that you have the moments here, yeah. So the moments and the pre-collision moments and the post-collision moments, yeah. And actually, you see whether you have the sum or the difference of the post-collision moments depends on what is the sum of m plus n plus l, right? So whenever we have a sum of these moments, they obviously turn into MAB over bar, and whenever we have a difference, they turn into this omega, right? So we can now rewrite this completely in terms of moments, and we call this equation now 8.4. By saying this is 0 is equal to the sum over m n l is equal to 0 going to infinity m factorial n factorial l factorial. So we still have delta x 1/2 n plus l, delta t half by the power of m. Then we have dt m, dx n, dy l. And now comes this moment. So we have m. Now it's now m a plus n, obviously, yeah, because this is the appropriate power in I. Then we have b plus l, and this is now the overbar version, yeah. This comes whenever m plus n plus l is an even number, because when it is an even number, then we have a minus left here that combines with this minus, right? And then we have the sum of the two, okay? You see this? Too confusing? It's a bit confusing. Okay, so putting this again. So you see this is the pre-collision moment, right? Yes? So this is the post-collision moment, yeah? MA plus N, B plus L, right? So now we want to solve the equation in terms of these overbar moments. And you see, this here always gives us the usual pre-collision moment, but this, the other one, gives us alternating whether m plus n plus l is even or odd. It gives us plus the post-collision moment or minus the post-collision moment, yeah? So now this is the pre-collision plus the post-collision moment, and this here is the post-collision minus the pre-collision moment. Yeah, so we get either this or this. Now, the case that we get this here comes with 1 minus 1 by the power of n plus l plus m. Okay, so let us see. So there's a 1 here, there's this minus here, and then we have this term here. Yeah, if this here becomes positive, then this here will be gone, right? If this becomes negative, then there's a plus here in combination. So we have actually both of them together. So we have this case. Now we also have the other case in the opposite direction. It is omega a plus n, l plus b, or b plus, okay, I should write it in the same order, not to confuse more than necessary. B plus L, and now because we add them, and together, and we have 1/2 here, and we don't have 1/2 here. We have actually to put this 1/2 here, right? So because otherwise they come up twice. So, and here it goes the opposite way. This only comes when there is not a 1 minus, but a 1 plus, minus 1 n plus L plus m. So you see, for any combination of n plus L plus m, you either get this moment or you get this moment here, but you never get both of them together. Yeah? Okay, now this is the Taylor expansion in moment form, in average moment form, for the Lattice-Boltzmann equation. And so you can do a lot already from this form. The only thing that is still annoying is that we still have the smallness parameters delta x and delta t in it, yeah, and we have to see how they can be separated. So you can do almost everything already from this stage, but we do one thing more. We introduce an asymptotic expansion. In the smallness parameter epsilon. So this is absolutely my favorite topic that I'm talking about in all of my lectures. Okay, so this is something extremely general that you can apply to, I would actually say, to all other numerical methods. There are a few exceptions where, for example, Monte Carlo methods, there does not work so well, this thing, but in all the other, say, deterministic methods, this usually works. So in order to have a numerical method, we have to have a smallness parameter. And the smallness parameter, depending on whether you are a physicist or a mathematician, they will call this in a different way. Mathematicians like to call it h. Physicists like to call it epsilon. Now, say we are physicists and say we call this epsilon. And this thing is discretization dependent. Small parameter. So what this typically is, but does not need to be, is the grid size. It can also be the time step. Now you already see the problem in Lattice-Boltzmann. We have both. We have grid size and time step. Yeah, we have to deal with this somehow. Or it could be something else. So then a numerical approximation in general, very general, numerical approximation looks like this. So you have a function phi of independent variable x, could also be time, doesn't matter. So some independent variable x and the smallness parameter is a function fx plus an infinite sum starting from, it should start from 1. If it starts from 0, then it's not a numerical method, but it's, so it's a power series, a power series in epsilon, so epsilon by the power of n times a constant times constants En, and this, so this phi, this is the approximation of a function that we cannot calculate. So this is the true function. So the entire purpose of numerics, I'm still audible, right? The entire purpose of numerics is that you want to calculate a function like the solution of a partial differential equation that you cannot solve. So you replace it by a different function that you can solve, and the true function is the f, and the approximation is this phi. And so since you cannot solve the thing, you always have this error term. Yeah? So you have this series of error terms. So now we never expect that we don't have errors, but we have some conditions on the errors that we would accept. So the method is called consistent if at the limit of epsilon going to 0, this phi, x, and epsilon goes to the true solution. Then we have a consistent numerical method. So this numerical approximation phi of x and epsilon is the truth plus a hierarchy of errors. Now we are assuming that we can write the error in this hierarchy, otherwise it doesn't work. Hierarchy of error terms. And these error terms are separated by powers of epsilon. So now this is an assumption that we are making. So in the concrete case, you also have to observe whether this is actually true, yeah, because your method could be inconsistent, or something could be, or the series may not converge, yeah. Then this may not be true. But this is the assumption on which numerical methods are usually built up. So what does this mean for our solutions? Say we have a solution for any moment, MAB, and we assume that we can write this thing as a sum from n equals to 0 to infinity over epsilon by the power of n, MAB of the order n. And the same thing is that we can assume this, that we also can write the other moments, so the collision moments, as a sum of the same kind, namely epsilon by the power of n into omega at the order of n. So, and the very, 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 very important thing here is that all the information of the smallness parameter is in this expansion. Yeah? So that basically means that the coefficients of this expansion, MABN of the order n and omega AB of the order n, they are not functions of epsilon. So this is really, really important. Yeah? So there is no hidden dependency. The dependency is just in this in the series expansion. Yeah? So the series expansion has coefficients, and these coefficients do not depend anymore on epsilon. That's important. So now, for example, the solution that we are looking for in the lattice-Boltzmann method is the density and velocity. Of the LBGK. So basically, we have a rho zero-order moment that we calculate, yeah, and this is made up of a zero-order term of this rho plus epsilon times the first-order term plus epsilon squared times the second-order term plus dot, 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 dot to infinity. Yeah? Equally, we have a velocity. So what we have here on the left-hand side is the thing that we can measure. Yeah? So the things on the right-hand side, we cannot measure. We only know what comes out. We don't know what is the solution and what is the error. Yeah? We only know the sum altogether. So this is u to the zero order plus epsilon to the first u to the first order and epsilon square u to the second order plus dot, 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 dot. So now this is our ansatz. Now we have to deal with one problem that I've just mentioned. We have two numerically small parameters. Now, this small parameter, basically error is cost, right? Error is a cost. So you could think about this smallness parameter as a sort of currency. Yeah, so you want to express your cost always with a certain amount that you have to pay. Therefore, it's as with currency, even though there are different currencies in the world. If you are in one country, you try to express all your expenses in where I come from in euro, and here you would like to have all your expenses given in rupees, right? So it is, you may agree that it would be difficult for you if there's one part of your life, so you have to pay your food in rupees and you have to pay your rent in dollars. Then you immediately would think, so how can I translate these two things? Yeah, but here in this numerical method, you kind of have the problem. So we have to pay in space and we have to pay in time. So what we like to do is to couple both of them together and just ask what we have to pay. And this means we have to make a statement of how delta x relates to delta t, so that we have only one small parameter. And this means this can of course be done in any arbitrary way. So we have actually an infinitely many choices how we could do this. Out of the infinite many, there are two obvious. Yeah, two simple obvious choices. I mean, or that look obvious, say. So what is most obvious? Most obvious is that you say that delta x is equal to your smallness parameter and delta t is also proportional to your smallness parameters. Just saying that delta x and delta t cost the same, right? That would be one possibility. So this has as a consequence that delta x divided by delta t would be independent of your smallness parameter. Is this good or bad? Who's for good? That this is good. Who's for bad? Okay, we have one person who thinks that this is not a good idea. So why do you think that this is not a good idea? Where's the microphone? Or you just made a okay. Intuition. Intuition is very important. Okay, well, we come to this. I see. We see. Actually, it's a trick question because it always depends on what you want to do. So it could be a good thing or it could be a bad thing depending on what you want to do, right? Yeah. So see the following. So the speed of sound, Cs, is here always given as 1/3 delta x by delta t, and this is a constant. Okay? So if you want to do acoustics, then indeed it's a good thing that delta x is proportional to delta t, because it means that the speed of sound is not a function of your discretization, which you don't want it to be, right? If you want to do acoustics. But maybe you don't want to do acoustics. Okay, so first observation, the speed of sound is invariant under scaling. So what we mean with scaling is that we change the resolution of the system. Yeah? So, and therefore, this is called acoustic scaling. So this thing, delta x is proportional to delta t, has a name called acoustic scaling. So let us remind that there are two dimensionless numbers in our Navier-Stokes equation. We have the Mach number. This is, of course, only for the compressible Navier-Stokes equation. We have Mach number. Mach is equal to U star divided by Cs. So okay, I'll call this now the physical velocity. Then we have the Reynolds number. This is the physical velocity scale times the physical length, the length scale divided by the physical viscosity scale, so physical length scale and nu the physical CS square 1 omega minus 1/2. So if CS square comes in units delta x, or if CS comes in units delta x by delta t, then we have to add here 1 delta t, and this is viscosity. So then anything?
Sir, you said two choices of delta x and delta t values will be there, is what you said. Right? What's the other choice?
There are two obvious choices, but right now we are just at number 1.
Okay.
So we come to the other one in a few minutes.
Okay.
Yeah. So this is still choice number 1. Choice number 1 is acoustic scaling, and we want to see what consequences this has on our definition of our parameters. Yeah. Because now we can write the Reynolds number in physical velocity times physical length scale CS square, CS square, and then 1 over omega minus 1/2 into delta t. So 1 over omega minus 1/2 delta t. So CS square still has its units. So we have we can actually replace this by the Mach number. Okay, did I do this correctly? U is the Mach number times CS, so we can replace this by the Mach number L asterisk CS, now without L square minus 1/2 into delta t. Now, as I said in the beginning, one important thing for us is that we want to do simulations, and in simulations, the Reynolds number should not depend on the discretization. So the Reynolds number must be independent of the crit size and the time step. So say now if the Mach number, the speed of sound, they are now independent of delta x and delta t. So this is the consequence of this acoustic scaling. So we can write everything that we know onto the left-hand side. So we have, that is not that we know, that is constant. So this is Reynolds number, the speed of sound divided by the length scale, and the Mach number is equal to 1 over omega minus 1/2 dt, means that 1 over omega can be written as L, the physical length scale, which is constant, times Mach number, Reynolds number times CS, 1 over delta t plus 1/2. So what did we discover? We discover that the relaxation rate we have to put here, this relaxation rate is a function of delta t. Yeah? So, because this here is scale dependent. Okay, very important in acoustic scaling. Epsilon, so acoustic scaling is epsilon is proportional to delta t is proportional to delta x. Then omega is a function of epsilon. This is very important in the expansion because I said in the expansion everything that, so the dependence on epsilon is just inside this the series expansion, yeah? So the moments themselves, they are not allowed to depend anymore on epsilon. Now problem is omega depends on epsilon. This means if you use this scaling, you have to expand omega. Otherwise, you don't get to the right result. And funny enough, this is by very senior mathematicians often simply ignored in the literature. So I have to point this out. So ignoring the dependency of omega on delta t in acoustic scaling is a persistent error in LBM literature. So I've spent the last 20 years on conferences and other to point this out again and again. And whenever I point this out to the authors who write this, they always agree on the spot and they always do the same mistake in their next paper again, because it's just so convenient to do this mistake. Yeah? So acoustic scaling, omega is not constant. If you assume omega to be constant, your analysis is wrong. And this is often the case. So there is another problem with this. In acoustic scaling, the lattice velocity or speed is not asymptotically small. Because we have delta x by delta t is actually constant. And this means, so we have a discretization. Remember, we have a discretization in velocity, yeah? In the lattice velocity. We have discretization, but we don't make this velocity small. So whenever we have any remaining error in velocity, and I think we discussed this when I made this assumption. U cube is considered to be small, right? So now we assume that delta x by delta t in this acoustic scaling is a constant. Then u cube is a persistent error because it will never get smaller even if I refine my grid and reduce my time step in this scaling. So this error will always persist, so it's not going asymptotically smaller, so you'll always have a finite error, so you have no convergence. So actually, acoustic scaling is intrinsically inconsistent. You don't get the Navier-Stokes equation if you start from acoustic scaling. LBM does not converge under acoustic scaling. This, of course, you can still use it. I mean, many people use it, acoustic scaling, because what you can do is you can add further assumptions. For example, just saying, yes, it does not converge, but our velocity that we start from is already so small that we don't care, right? This you can say. You still don't have convergence, but you may just be happy with your method, okay? So actually it's used a lot, even though it is known that it's not consistent. So if you really want to have consistency, you have to do something else, and this something else is called diffusive scaling. Diffusive scaling. So, and now what we want to do is we want to keep this omega at a constant so that we don't need to expand it. I mean, constant in the sense that it's scale independent. So for this to work, we have to look at the Reynolds number, U star times L star divided by CS square 1 over omega minus 1/2 into dt. So this, of course, the Reynolds number has to be constant, but we also want to have omega equal constant. So now we take what we've actually already introduced, the CS square. We define this as theta, dimensionless, which we call the dimensionless temperature, into delta x square by delta t square. So this guy here is dimensionless. And it has a physical meaning of a temperature. This is why we call it the dimensionless temperature. So now we can rewrite this with U star L star divided by theta dx square dt square 1 over omega minus 1/2 into dt. So what you see here, if you want to have omega being const, then this would be the case if delta x square is proportional to delta t. Delta x square proportional to delta t. And for CS, this now means this is square root of theta dx and divided by dt, so proportional to, now theta epsilon divided by epsilon square, which of course is square root, sorry, what I'm doing, 1 over epsilon. and this is the limit for epsilon going to 0, Cs is going to infinity. So this means we send, by this scaling, we send the speed of sound to infinity. When we send the speed of sound to infinity, we send the Mach number to 0. Now we are approximating the flow at Mach number 0. And when we approximate it at Mach number 0, we actually solve the incompressible Navier-Stokes equation. Yeah? So we get convergence. So yes, because the simulated velocity now gets asymptotically small. So actually now it's true if we have an error term that is u cube somewhere in our results, and we refine the crits, then this u cube error actually goes asymptotically to 0. It will vanish. Right? For smaller and smaller crit spacing, this error becomes smaller and smaller and smaller compared to the solution. Right? So the simulated velocity is asymptotically small. Compared to the speed of sound. To the speed of sound and the lattice velocity. So, of course, now this means that the Mach number is no longer scale invariant, and if you want to do acoustics, this is not a good idea. So they always say you have to die one death. Yeah? So with acoustic scaling, you can simulate acoustics, but you have inconsistency. With diffusive scaling, you have consistency, but you cannot simulate acoustics. So now we have to express our physical speed, the one with the star, as dimensionless speed times delta x by delta t. So this gives us the dimensions. Actually, this is proportional to epsilon, and this here now is dimensionless. So yes.
So this delta x and delta t, they are in still lattice units, right? They're not physical.
Now delta x and delta t is, if you do the translation, they are now, of course, physical units. So we express, so the idea behind this is we express this u in terms of delta x and delta t. So meaning in the calculation, if we have a speed of 0.1 lattice spacing in one time step, this becomes 0.1. Yeah, so this is now our dimensionless velocity in terms of lattice units. Whereas this is the translation factor, so this is actually delta x in meter by delta t in seconds. Yeah? Because, I mean, I see there can be confusion. That this here is given in lattice units. Yeah. So out from this perspective, delta x is 1 and delta t is 1 because it's given in that units. Yeah. For the physical speed, this delta x is, of course, the length scale that you have given to delta x, and dt is the time step that you have given. So that's the translation factor. So lattice, this here is in lattice units. This here is in physical units. Is okay? So maybe I'll briefly recharge. So yes, so what does this mean for our, I need to. So the U that comes out of our simulation now will now be written like this. So there is a U to the 0 order plus a U to the first order. Now we see that this translation factor here, delta x by delta t, this is already in epsilon. So we have the solution that we have itself changes with epsilon. This means that this constant part, the constant part does not change with epsilon. So this here must be set to 0. Yeah? Because if this was not the case, we would have an error term that is asymptotically larger than our results, which is obviously inconsistent because there's no way to separate them, right? So we have to set this here to 0. Then, which we'll see is our choice, because we can set the initial condition and the boundary condition of U0 to 0, meaning that we have to make the initial and boundary conditions dependent on the resolution, right? So, and then we have these higher order terms. So going on. So these here will be our error terms. Now we will put this expansion, the asymptotic expansion of the moments, into our equation 8.4, and because we have discussed now for such a long time about asymptotics, that okay, so we put this in diffusive scaling. We start from our equation 8.4. So, because we have not seen equation 8.4 for some time, I rewrite equation 8.4 because it's a little long and a little confusing. It's 1 over m factorial n factorial L factorial. So it's the same equation that we had before. I just write it again. So this delta x divided by 2 in n plus L, dt m dx n dy L m a plus n b plus L. So this is the overbar version, 1 minus 1 n plus L plus m minus omega a plus n b plus L 1/2, and here comes 1 plus minus 1 n plus L plus m. So, and I hope this is the same equation that we have written before. Now we enter the asymptotic expansion of this moment and this moment here. Then we call this the equation 8.5. So we start from 0 equal to the sum over m, n, and L equals to 0. And now we also have to enter the expansion of the moments, and we call this Q. Q is equal to 0, and all of them go to infinity. M factorial, n factorial, L factorial. Now first we have to deal with this part here, yeah, where we have the delta t by the power of m and delta x by the power of m. Now delta t is proportional to delta x squared, right? So if it's delta x squared, it needs to be epsilon by 2m, right? And then the others, n plus L plus, and also there comes now the Q. So the Q comes from the expansion of the moments. So we are going to expand these moments, and in this expansion we also have the Q. This is why I put everything together here. So then we have to look at this part down here. This is 2 by the power of m plus n plus L. So note, this is not a mistake. Yeah? Here's 2m plus n plus L, and down here we have m plus n plus L. So here's 2, here's no 2, right? That's not a mistake. Then the time derivatives, the spatial derivatives, and now here, so this is the thing that has been missing so far. A plus n and b plus L. So this is over bar, and now this is the Q. This is order Q. Yeah. So this is why we have to multiply with epsilon by the order Q. Epsilon by Q times m order Q, right? And we sum over all of them. You get it? 1 minus 1 n plus L plus m. Now comes the same thing for this omega. This goes to order Q. This 1/2, 1 plus minus 1 n plus L plus m, and closing brackets. Okay. So now, so far we make everything more and more and more complicated. Now we want to start to make things simpler, yeah, to actually use this for making life simpler. So far, this looks like everything is going complicated. Yeah, so what we know is that this equation 8.5 is equal to 0.
What is Q there?
Q Q is the expansion coefficient of the moment. If I may just go back. You see, yes, unfortunately I called it n here, but I've used n already. So we expand, so we have this moment, and this moment is expanded in the series, in the power series of epsilon by, now say q, yeah, times the q'd order of MAB, yeah. So this sum is now included into this. I don't want to write 4 sums here. Yeah, clear? So okay, so all of this is 0, and now what we are doing is we are doing some equating of coefficients. Equating of coefficients is a very important thing in any analysis of numerical methods. You see, this entire equation is supposed to be 0 for all choices of epsilon larger than 0, right? Because epsilon is a smallness parameter. It's supposed to be small, but it's otherwise arbitrary. And it's positive. And being small also means it's not 0. If it's 0, then we don't have a resolution. Yeah? So, small but not 0. And this equation here will be 0 for all choices of epsilon only if each order, epsilon, say epsilon p, is 0 individually. Yeah? So you know equating of coefficients, say a plus b epsilon plus c epsilon square. You say this is 0, yeah, for all epsilons larger than 0. Then this can only be the case if a is equal to 0, b is equal to 0, and c is equal to 0, right? This is what we call equating coefficients. Very important step. Because this means that each individual order in this, where we have epsilon to the same power, yeah, we can organize this to epsilon to the same power, and they will all be equally 0. So I already organized them all together, right? So I could say that whenever, all the terms, when 2m plus n plus l plus q have the same value, then the thing is 0. So I can rewrite my sum in this following way, that 0 is equal to m n l is equal to 0. So I'm not writing to infinity here. Yeah, I'm writing, rather than now q is p minus 2m minus n minus l for any given order of p. Yeah, so any order, so p is the order at which I look at these equations, at the equation. Yeah, so p basically is, yes. So I mean, if p is equal to, so this is what I said. If p equal to this, all of this is the same. So I'll provide a p. Yeah, so p is something that I have to give into this. Then I count m n l up, and then out of this I can automatically compute the q that gives us. Yes, I can automatically compute the q, and the rest of the equation stays the same. So I don't need to include this here anymore because this can be factored out. The only thing I have to include here is 2m plus n plus l, and now comes dt m dx n dy l. And what is left here is m, a plus n, b plus l, over bar this to the order q, 1 minus 1 n plus l plus m, minus omega a plus n, b plus l, divided by 2, 1 plus minus 1 n plus l plus m, and closing all the brackets. So now you could count these things up to infinity and find that you go to I mean, if you count m and n and l up to infinity, then what happens is that Q simply gets negative, right? Yeah. So, but in our expansion, we had only positive orders of omega and m. So what we have to assume here is that these guys are 0 for all Q smaller than 0. Yeah? So this sum is automatically terminated. So what does this help us? Now we have to assume a certain value for P. A certain value for P, for example, P equal to 0, means we look at the part of the equation that comes with epsilon to the power of 0, right? So if we put epsilon to the power of 0 here, then we see we cannot be, so P is equal to 0, yeah? So this only works when M, N, and L are also equal to 0, yeah? So we don't actually get this part here because we take this all to 0. It's 1 minus 1, this disappears. Here we have 1 plus 1, yeah? Oh, forgotten to write Q here, right? So 1 plus 1, so this is 1/2. So what comes out is we get minus omega AB to the order of 0 is 0, okay? So this looks trivial, but it's very important. It means that whenever we have this collision moment to the order 0, we can replace it by 0, yeah? So for any A and B, yeah? So then we put P equal to 1. So this is basically all the equations that come with epsilon to the power of 1. Here we have now more terms, namely delta the derivative of. So we actually get this moment here to A plus 1 B. Okay, we don't need the brackets. B. So this now comes to 0 order because we have to count up here 1, yeah? So N is 1, so then Q must be at least, so P is 1, N is 1, so Q is 0. You see it? Plus dy M A, so the similar here, plus B plus 1 to 0 order. And this goes into AB to first order now, and this is together, this is 0. Now, I said that our solution, I mean, this is now our choice, basically. But our choice was that our solution comes at first order, so the velocity solution comes at first order and not at 0 order. So this means that we may have something at 0 order, but whatever we have at 0 order would be constant. And constant means it's not dependent on space and time. So if you take the derivative, they will disappear. Yeah? And so these things here are 0, which means that this collision moment to first order is 0. Now we know that it is 0 to 0 order, and we also know that it's 0 to first order. I'm potentially taking overtime, I guess. Now when we start 10 so okay, so 2 hours I still have. Okay, so maybe not very amazing. Go on. P equals to 2. So the equation for epsilon to second order. Now comes the first time that we have a time derivative here. You see, because we have to we didn't have a time derivative previously, because if we have 2m, yeah, if we have p is equal to 1 and minus 2, yeah, so we get to negative and we have no negative expansion moment, so there was no time derivative here, but now p is equal to 2 and m can now be equal to 1, so then q is equal to 0, which means in that case we would have dt m ab. So this thing here equal to 0, but we have just said that this here is constant. So if it's constant and we take the time derivative, it will disappear. And it's gone again, dy ma. Now we get here this to first order, b plus 1. So to first order, it's in general not 0. A plus, what am I doing? Oh, yes. Okay, I wrote the y first, sorry. Yeah, maybe. So I wrote the y first to see whether you're awake. No, because I was stupid. And this goes into now AB, the second order. This is equal to 0. So what we observe, even though this guy here is 0, but the second derivative, the omega AB to second order itself is independent of the time, but it's not independent of the space, and so it's not 0. So we want to solve an equation that is dependent on time. So we still have to go on and say that p equals to 3, meaning we are going to epsilon to the third order. And now comes here the first time dt MAB to the first order, which is not constant, right? Plus dx MA plus 1b. This comes to the second order plus dy MA 2 second order b plus 1 minus omega AB to third order equal to 0. So what I'm not going to write here is that we would also get the second derivatives of a forced moment to 0 order. But we said that the moments at 0 order are constant, so I don't write out that we get also this higher derivatives of zeros here, right? So this is the last equation that we get at third order, and here we have already the time derivative in it. So now we can assume that this is all we need to derive our Navier-Stokes equation, and now we have to get a little bit more specific, because what we have not yet determined is what A and B is, right? So, specific. We say we are in epsilon square, and A is equal to 0 and B is equal to 0. Okay, so what do we get? We get dt m 0, 0 to 0 order plus dx m 1, 0 to first order plus dy m 0, 1 to first order minus omega 0, 0 to second order, and this is equal to 0. So the 0 order moment is the mass moment, and this is conserved. So if it's conserved, then the collision of this is obviously 0. So this is 0. Also, this is a derivative of a moment to at 0 order. So this is constant. Yeah, it's okay. It's not the moment itself is not necessarily 0, but it's constant. So its derivative is 0. So these things disappear. Yeah, this, I mean, we can write it down. M 0, 0 to zero order is rho to zero order. This is constant. We have m1 0 to now first order. This is rho to zero order and u to first order plus rho to first order and u to zero order. U to zero order is 0. Yeah? So this rho to first order disappears, and all we have left is rho to zero order times u to first order. I mean, by this, you see, this is different from a lot of other analysis methods. And the asymptotic analysis can be applied to nonlinear functions too. Yeah? You only have to take care that here the sum of these orders gives you the order that you have on the other side. Right? So because you're expanding rho in epsilon and you're expanding u in epsilon, and you're looking for the case now that together they come with epsilon here, with epsilon to the power of 1. This is the case if rho comes with rho zero order times u first order, or rho first order times u zero order, right? So obviously the same thing for this guy, rho zero order and v first order plus rho first order and v zero order, and this again is 0. So the entire equation then becomes dx rho to zero order u to first order plus dy rho, what am I writing? dy partial y rho to zero order v to first order, and this is equal to 0, meaning what we've discovered is, can write this as rho to zero order is constant, so we can put it in front of the derivative. Divergence u to first order is equal to 0. Okay? Now, this is the first equivalent PDE that we observe, and we observe that this is the incompressibility condition, and we see that under this scaling we get the incompressible version of the Navier-Stokes equation out. So, okay, so the first equivalent partial differential equation we got. Let's see whether we get the momentum equation. We take epsilon to the power of 3, and we take a to a as 1 and b equal to 0. So, and this gives us equation 8.6 dt m10 to first order plus dx m20 bar to second order plus dy m11 to second order minus omega 10 to third order is equal to 0. Okay, please.
Why u to the power of order 0 is equal to 0?
Why?
U and v to the power of, I mean.
No, not to at the order 0. You mean this here?
Ah, yes.
Yes. So because we decide that they are. Okay? For this, let us. So we have under our control what we set as initial and boundary conditions. And in order for this, so what we need to do is that the velocity, the lattice velocity is going down when we refine our grid. Yeah, this is because we have delta x. Delta x is proportional, so delta t is proportional to delta x squared. Yeah, so the velocity needs to get smaller and smaller. So this means that the that the solution of our equation already needs to be dependent on epsilon. Yeah? So then this means that the constant part, so the one that is not is not dependent on the resolution, this we set to 0.
Just the assumption that we are making.
Yeah, it is an assumption that we are making, but this is a degree. Our assumption is a degree of freedom, because we can set this in the initial and boundary conditions. We have to set our initial and boundary conditions such that there is no constant part in the velocity. Yeah? Or no part in the velocity that does not depend on the resolution. Yeah, so then we set this thing here to 0. And because we set it to 0, we have it 0. If you made a different, this is a requirement of the diffusive scaling. In acoustic scaling, this is not true. In acoustic scaling, this thing here, your solution would be in order 0. But then the other orders would not disappear. Yeah? It's a decision that is a design decision for our method. That the zero order part of this expansion is 0. So it's both an assumption and a design. So now at this point we are a little stuck, because we have to evaluate the second moments, and they require the calculation with the BGK collision operator. So we remind ourselves that we have this AB over bar is equal to AB asterisk divided by 2, and this AB asterisk is AB MAB plus omega MAB equilibrium minus MAB. So this is our BGK equation that I call 8.7. Omega AB is of course omega AB after collision minus omega A minus MAB after collision minus MAB before collision, meaning that we can write MAB as MAB over bar minus omega AB half, and the other one we can write as MAB over bar plus omega AB 1/2, and we can put this into this equation 8.7 to get MAB over bar plus omega AB. So we want to express everything in this over bar version. MAB over bar minus omega AB half plus omega MAB equilibrium minus MAB over bar plus omega AB half. So what you see is you can eliminate these things, and then you can rewrite this omega AB as being small omega MAB equilibrium minus MAB over bar plus omega AB 1/2. So this is this implicit formulation, and this can now be reintroduced and made explicit in MAB being MAB over bar being MAB equilibrium minus 1 over omega minus 1/2 omega AB So, and I may have been a little quick here, but we have done this already several times. So you see we have this Heon correction 1 over omega minus 1/2 in front of this omega AB, and this we put into our equation 8.6 to get the following. So we have dt rho 0 u1. So this is the first moment to first order. Yeah, I don't write the other version that we've just discussed again. So this is what is left. Then comes dx. So we get m20 equilibrium, and of this we get the second order minus 1 over omega minus 1/2 omega 20. We get of these the second order plus dy m11 equilibrium to the second order minus 1 over omega minus 1/2 omega 11, also this to second order, and there's a reminder that is the omega 13 to third order, and all of this together is 0. So we know what is m20 equilibrium to a second order. This comes from the Maxwell-Boltzmann distribution. So there is the speed of sound squared. Now, because we have gone non-dimensional, I write the speed of sound non-dimensional as the non-dimensional temperature theta. Theta into rho to the second order now, plus u to first order square rho to the 0 order. Now, please be aware, as I said, this works for nonlinear functions too. Yeah, we had to expand u in terms of epsilon. Yeah, and we are looking for the terms in second order. Yeah, so we get this by the first order of u squared is the second order. Yeah, because we have to have epsilon squared in this. It's clear? So this is the equilibrium of this m20 moment, and we have m11 equilibrium to the second order is u1 v1 and rho to the 0 order. Now we put these guys into the equation again and put this as 8.8. So this is dt rho to 0 order, u to first order, plus dx. Now comes the equilibrium part here, theta rho to second order plus u to first order square, rho to 0 order, plus dy u to first order, v to first order, rho to 0 order. So this was all the equilibrium part. Now comes the non-equilibrium part, minus 1 over omega minus 1/2. So the Heon correction into dx omega to 0 to second order plus dy rho omega 11 to second order. This minus omega 10 to third order. All of this is equal to 0. Now we have to know what is this omega 20 at second order. So, but we know how to do this because we have our generating function. Yeah. So all we need to do is to look at epsilon to the second order. Yeah, looking at second order, and a equal to 2, b equal to 0. That should give us the correct moment. So again, we have dt m20 at 0 order. So we know that this disappears because this is constant in general for all the moments. Then plus dx m30 to first order plus dy m what indices? 2, 1, and here again to first order, minus omega 2, 0 to second order is equal to 0. So by this we can rewrite, obviously, that omega 2, 0 to second order is equal to dx m30 to first order plus dy m21 to first order, and this is this is equal to dx m30 equilibrium to first order plus dy m21, no, not this over bar, just equilibrium to first order. Can anybody explain me why? Why this is equal to the equilibrium now? So what is non-equilibrium? We have equilibrium plus omega, right? Equilibrium plus omega is would be the non-equilibrium. We have seen that omega is 0 at 0 order and at first order. So because we are talking first order here, this could only contain the omega at first order, and the omega at first order is always 0. Yeah, so then it must be the same as in equilibrium. So what is M30 equilibrium at first order? We are only talking first order. First thing is we know it's an alien, right? Why is it an alien? Okay, you're sitting in the middle, so I always look at you. This is an alien. M30 is an alien. What was an alien? It's dependent. Yeah, on what does it depend on? 1. It's 1, 0. So it's the same as 1, 0, right? So we know what this is. So this is rho 0 times u1, right? So we already know this. Yeah, okay, I should write what I just said. This is 0. Yeah, so this is the reason for this. So then M12 equilibrium at first order. So what is this? We know about defactorization. So it is actually a factorization of equilibrium. So it's M10 times M02. Yeah, but it's only at first order. So it's at first order. So okay, so we have M10, which is already first order. So there could only be a part of 0 order of M02. What is the 0 order of M02? Actually, we had this equilibrium up here, right? So we have a u square in it, and we have theta times rho. Yeah, but here we have theta times rho 2. Here this can only mean theta times rho to the 0 order and u to the first order. The same thing, by the way, is this here. So the first order is equal to theta times v to the first order times rho to the 0 order. And all of this now go to 8.8. 8.8, and give us the following equation. So 0 is equal to dt rho 0 u1 plus dx theta rho second order plus u first order square rho 0 order plus dy u to the first order v to the first order rho to the 0 order. So this is the equilibrium part that we had before. Now comes the non-equilibrium part. This is minus 1 over omega minus 1/2. Now we plug into this dx omega to 0. Yeah, we plug in here these guys here, and we take this derivative or that derivative together with these derivatives, and I've already reordered them, yeah, to get to an end now. So it's the second derivative in x to the first order rho to the 0 order plus dy y theta u to the first order rho to the 0 order plus dx by 2 u to the first order theta rho to the 0 order. So by this I combined everything that went with dx and dx and dy and dy, and also the mixed parts dx and dy. And this ends in having omega 1 0 to the third order, and all of this is equal to 0. Now I'll call the entirety of this, I call A, and say that A is equal to rho 0 theta, so this is what I take out, dxx u1 plus dyyy u1. Yeah, so this is what I take out, because this is what I want to have. So I want to have a Laplace operator on the velocity, because this is what I want to see in my Navier-Stokes equation. And the thing that I do not have, I'll take this out into dx in dx v to the first order 1 minus theta rho to the 0 order plus dy 2 v to first order theta rho to the 0 order. Now this here is what I want to have. This here back here, this is what I don't want to have. So I call this guy here B. And since I don't want to have it, I say that B is supposed to be 0. And what I'm going to use is that we know from this expansion that we made is to first order the divergence of u is equal to 0. So this we can use if this 1 minus theta is equal to 2 theta, yeah? So this would just be proportional to the divergence of u, right? So then we can write that 1 minus theta is equal to 2 theta, and this implies that theta is very surprisingly 1 over 3. which we have now derived in three different ways. So finally, we get to the Navier-Stokes equation, dt rho to zero order u to first order plus dx u first order square rho to the zero order. So this here is the material derivative. Okay, so not that this hasn't been the entire there's still one part missing. V1 U1 rho 0 equal to minus dx theta rho to second order. Now you see that theta rho to second order, we have the second order as the pressure plus theta rho 0. Okay, I'm going to write this in the next line, it's better. Plus theta rho at zero order 1 over omega, which is not a function of epsilon, dxx u1 plus dy u1. So this, all of this together here is viscosity. And the one thing I've not yet written is 1 omega 1 CL3. So can anybody, and okay, we have already this is the Navier-Stokes equation, but can anybody tell me what this omega 1 0 to the third order is? Okay, it's 0. Why? Because? No, why is this here 0? You are right, but it's a trick question, so you can be right. Why would that here be 0?
No, my logic was if it is not 0, then we will not never. We never.
We will not have the
Navier-Stokes.
Navier-Stokes, so you can set this to 0 because it's a conserved quantity. But in the Navier-Stokes equation, we have this thing, and we call it body force. Yeah. So this is a source term for the momentum. Yeah. So for example, if you have gravity, if you have gravity in the system, yeah. So then there is a constant part that you add on top of the momentum, yeah, and this is what we call the body force. Okay, so this is exactly 2 hours on the asymptotic analysis. So the asymptotic analysis is one of the more powerful ways to do the in-depth analysis of a numerical method. Can be applied to other numerical methods too. It works for nonlinear systems, and it gives you directly the partial differential equations that you want to solve, yeah, with their orders where they appear. And the nice thing is you can also derive partial differential equations for your leading order error. Yeah? So this would be like, because now we have a second order accurate scheme, which we have not proved, but which is the case. So second order accurate means that every second order in this expansion does not appear. So if you had looked very, very carefully, you may have noticed that I did not write down rho to the first order where there would actually have been a rho to the first order, but there is no rho to the first order. Rho only comes to 0 order, second order, fourth order, sixth order. Yeah, and the solution is at second order and the first arrow is at fourth order. Velocity the same. Solution comes at first order, first arrow is at third order, which you can prove by deriving the equations and see that they are zero. Yeah? So here you can directly derive equations for these arrow terms, and by such that you can analyze these arrow terms in particular detail. And by so doing, you can actually find ways to get rid of these arrow terms, which also leads to higher fidelity, but which is something that you then, after you've learned this course, have to read in the literature, because this would go too far and we cannot capture this in this week here. Okay, so the way it is now proceeding, I'm not completely sure, because we have done most of the preparation for the hackathon, which will be tomorrow. You now get some time to finish, if I'm not mistaken. Yeah, you now get some time, if you have not prepared your code now, to prepare that it runs with BGK and a lid-driven cavity, because what we are going to do tomorrow, and it will be in the afternoon, so this is another change from the schedule. We'll have it at 2 o'clock in the other room, where we can sit together, form groups of 4 people. Yeah, and I encourage you to already, probably not go your best friends, because we want to mix you. Okay, we think about a system that this works. So the idea is that different people of you with different experience, and unfortunately, I don't see it from your face how much experience you have. Yeah, but we want to get people with different experience together, so that the groups are a little bit more symmetrical. And then what you're going to do tomorrow is we challenge you with asking you to implement a different collision operator, which will be some multiple relaxation time collision operator, but with a few details just that we're going to tell you then. And for this, you need to have already a running BGK code. So this is what we like you to do, and then finding people together is, we have not yet decided whether we keep you the complete freedom, but if we see that people cluster together because they know each other too well, we may rearrange those. Yeah? Okay, so this was before asking about questions, right? So are there any questions? So the more questions you ask, the lesser time you have for preparing your code. If you're already done with your code, then you can ask questions. So if not so, then I'm not completely sure about the schedule, but we should have a break, right? Yeah. We should have a break of a few minutes, and then we continue with the code. We will be around. If you have any questions and problems, then we can discuss this. So it's important that by tomorrow you have a running code. Okay. And thank you for coming.